Today I will be talking about this polynomial time approximation algorithm for counting words accepted by a non-deterministic finite automaton. Let me tell you that this is joint work with Luis Alberto Croquevielle, Rajesh, Jayaram, and Cristian Riveros. So let me show you one of the motivating scenarios for this problem. Here we are given a graph database. In a graph database is a node and edge label graph. So we just use, in this case, labels in nodes to represent people like Paul and Jack. And we use edges and the labels in these edges to represent a relationship between these people. Like John knows Paul and Paul is a friend of Jack, right? This is a very common scenario, and today actually graph databases are very popular. So a canonical way to query a graph database and to extract a particular path from graph databases is by using regular expressions. In this case, we have a very simple regular expression that says I would like to construct path such that the label of this path conform to this regular expression here, which is, well, friend plus knows star, right? So one possible answer to this query is this path here, which is a path of friends, and another answer is this path. I mean, the path that you can see in the right-hand side. Again, it's a path whose labels conform to this regular expression. And then obviously, I mean, if you want to retrieve path, you usually specify the length of the path that you want to retrieve. This is also a common functionality. And something that is important here is that if you take the main graph databases today, in all of them, you will have regular expression as a way to extract path from a graph database. So then, once you have specified the length of the path as a parameter, you have two fundamental problems, apart from retrieving all paths, but usually you don't want to do that because you will have way too many paths. What are these problems? The first problem that you can see here is count. This is count of GRN. So the idea here is that you are given a graph database, a regular expression, and this length n, and just a technicality, but this n is given in unary. And what you want to do is to count the number of paths P in G such that P conforms to regular expression R and the length of P is N, right? And also another important problem is this problem gen with the same input, but now you want to generate uniformly at random a path P in G such that P conforms to R and the length of P is N. And in particular, this second problem is very interesting in the sense that you can think of given fair answers to a query, right? I mean, I give you a regular expression and I want to give you a path that is somehow representative or is taken from the set of all possible paths actually that conform to this regular expression. So count is a sharply complete problem, so we cannot hope for a polynomial time algorithm, so only approximate solutions are possible, and the best known approximation work in quasi-polynomial time. So the motivation for this work was to improve this algorithm and actually to construct a fully polynomial randomized approximation scheme for this problem count. And well, this is a very well-known concept in STOC, obviously, but I mean, let me just recall the definition. So the idea here is that we want to construct this algorithm B that receives as input a database, a graph database G, a regular expression R, a length N, and an error epsilon, right? And the idea is that if the relative error of this algorithm, so what we want actually is a randomized algorithm. We want this, we say, well, we want the relative error of this algorithm to be at most epsilon, but with a probability that is at least 3/4, right? This is the usual definition. And also we want B to work in time polynomial in the size of the input, which in this case is the size of the graph, the regular expression. N is given in unary, so it's the size of this, which is N, and more importantly, 1 divided by the error, which is epsilon. So, and the idea of this talk is to give you an idea of how this fully polynomial time randomized approximation scheme is obtained, and hopefully give you all the details, obviously not all the calculations. And the first important thing is that count can be reduced to the following problem. So the input of this problem is an NFA, a non-deterministic finite automaton A, a length n, again given in unary, and an error epsilon. And then what you have to do is you have to count the number of words W such that, well, W is accepted by the automaton and the length of W is equal to n, right? And notice that in this case, in the previous problem, we have a graph database and a regular expression, but just translating this regular expression into a non-deterministic finite automaton and doing a cross product, you can just reduce to a non-deterministic finite automaton A. And okay, just the notation that we'll be using in the talk, which is a standard notation, we will assume that Q, I will use it several times. I mean, Q is the set of state of this automaton A. The alphabet is a binary alphabet. Delta is the transition relation for this NFA. I is the set of initial states, and F is the set of final or accepting states. So then again, so this is the problem that we want to solve actually, and I will be using this notation a lot. So this L sub n of A is just a set of strings accepted by the non-deterministic finite automaton A of length n. And then the task is to compute a number n that is a 1 plus minus epsilon approximation of this set here, right, of this L sub n of A, and which means in particular actually that n should be bounded by below by 1 minus epsilon times this quantity and above by 1 plus epsilon times this quantity. And besides, well, number n has to be computed in time polynomial in the size of this of the input. And for the input, well, we have the length n, we have 1 divided by epsilon, the error, and we have m. I will be using this m a lot also, right, where m is the number of states of the automaton. So, okay, so let me give you the components of the algorithm. The first component is very simple. We need to unroll the automaton A, which essentially means that we want to eliminate cycles, right? And this is a very simple process. What you do is you for every state Q of the automaton A, you include copies Q sub 0 to Q sub n. Remember that n is the length of the words that we want to count. And then for every transition, you say, I want to go from a layer to the next layer, right? So for every transition PAQ in delta, what you do is you include the transition P sub I, A, Q sub I plus 1 in this unrolled automaton. So you're saying, I want to go from state P at layer I to state Q at layer I plus 1. Right, and besides, you eliminate from the unrolled automaton all the unnecessary state, right? So you can assume that for each state Q sub I that is in the automaton, you will have a path from an initial state P0, right? And remember that P has to belong to I. This is the set of initial state of the automaton A, sorry, and P0 is just an initial state. I mean, this is very simple. And then the important part, I would say, is that now what we need to do is the following. So define this L sub Qi as a set of a string W such that there is a path from an initial state P0 to Qi labeled with W, right? So you're saying, I want to, in this set, I want to have all the words W that if you start from an initial state P0 in this case, well, you will reach this Q sub I, right? Q sub I is the ending state in this case, right? And notice that the length of W has to be I, right? Because you're saying I want to go to this Q sub I starting from an initial state P sub 0. And for every subset of Q, right, also we will be considering sets of states. For every X, which is a set of Q, we will use this notation L sub Xi, right, as this set here, which is the union for every state Q in X. And again, actually, I'm not trying, okay, not to confuse the notation. When we use Q, we are talking about the states of the original automaton, and the Qi are the states of this unrolled automaton, right? So what we're saying is we take every X is a subset of Q, so we take every Q which is in X, and we take the union of these sets L of Qi. Okay, and then the task, the final task is to compute, remember that F is a set of final states. We want path of length n, so we have to consider this set Fn, and we want to compute an estimation of the size of this set here, this L of Fn. Okay, so how does this work? So the idea here is the following. We will need this parameter kappa, which is, notice that is polynomial in n, m, and 1 divided by epsilon. And what we want to do is, in order to estimate this number of paths, we will maintain a data structure. And in this data structure, we will keep two things, actually. We will maintain some approximations, but also some set of uniform sample. So in particular, what we do is the following. We say, well, this n of qi, it's an approximation of this set L of qi, and it's a 1 plus minus kappa to the minus 2 to the I approximation. I mean, really, this number is not that important. It's something that you need for the calculations. But notice that when we are at higher layers, actually, this approximation will be worse, right? I mean, because the I will be growing, right? And also we have to maintain at each layer I, and for every state, this set S, which is a multiset, so we will keep duplicates. And this S of Qi is just a multiset of uniform samples from L of Qi of a certain size. And the important thing is it's a polynomial size. Again, this is 2 times kappa to the 7, and it's just because we want all the calculations to work, right? But the important thing is it's a polynomial size in kappa, which again is polynomial size in m, and 1 divided by epsilon. And then we have this structure to be inductively computed, which is this sketch of I, where we keep all these estimations n of qj for every j in between 0 and I, and also this multiset S of qj for every j in between 0 and I. So, okay, so this is the algorithm template, actually, how it works, actually. Again, we start by unrolling the automaton. Then we compute for every initial state these initial values that we are inductively constructing, right? This n of q0 and this s of q0. And in this particular case, this can be obviously constructed. Actually, this n of q0 is equal to 1. We have epsilon as the only string in this language, L of q0. And we have S of Q0 as the empty string. I'm using lambda for the empty string, not to confuse with the error epsilon, right? And then how's the idea of how the algorithm works is as follows. What we want to do is then for every I in between 1 and n, and for every state, first we compute, and I will tell you how, this n of qi, given this sketch for the previous layers. So we have a sketch of I minus 1. And then we sample, and once we have computed this nqi, we sample polynomially many uniform elements from L of qi using this n of qi and this sketch of I minus 1, and we define this as the set S of qi. And then finally, we have to return an estimation of this L of fn, right? Set, I mean, an estimation of the size of this set of words accepted by the automaton of length n, given this sketch of n. So this is the template of the algorithm, and now I will show you how these different components work, right? Okay, so let me use the following notation. We use the notation n of xi for an estimation of this set, right? This L of xi. And remember that x, I'm using x for a set of states, right? And such an estimation is not only needed for the last step when we need to estimate, we need this to compute this n of fn, it's also using in the inductive construction of this sketch of I. Okay, so first simple observation, well, notice that this L of xi is not equal, obviously, to this sum for every p in x of L of p sub I, right? Because this L of pi are not necessarily disjoint, right? Okay, but this can be easily solved. I mean, you can, if we assume that we have some linear order on the states, right? Something that we can do is we can say, well, then the size of the set Lxi is just going to be equal to, well, you take a state P, and what you have to include in this summation is, well, L of Pi minus the L's of all the states that were before this state P according to this order, right? So essentially I'm saying A union B is the same as A union B minus A, right? Okay, but what is important here is that once we have this simple idea here, actually, so we could consider actually, okay, I'm just multiplying and dividing by the same number here. But the important thing here is that then what we are going to say is there is a way to do an estimation of this quantity. And how we are going to do this is, well, we will have an estimation for this LPI, which is this NPI. So we will replace this. And in order to estimate this ratio, actually, what we're going to do is we're going to use this sets SPI, right? So, and we will use, instead of this quantity here, we will use this quantity here, right? This SPI and in the denominator and in the numerator and the denominator, right? And this is what we call N of Xi. Okay, obviously I haven't shown you why this is a good estimation, but the key idea here, okay, first of all, notice that this set here can be computed in polynomial time, and this is a simple observation, but it's very important. And the way to do it is just, you have a polynomial number of elements in S, and for each of them you have to check that you are not included in these sets, which is something that you can do, right? Because what you are doing is saying, okay, it's not possible to reach Qi from an initial state in the automaton. And this is something that can be checked, right? Okay, so then what guarantees that Nxi is a good estimation of this set? And here is the main property to maintain. And this is really the main ingredient of the algorithm. We call this property E at layer I. We say that this holds if for every possible state and for every subset of states from Q, the following property holds. This is the quantity that we want to compute in the previous summation, and this is the estimation at what we want. And notice that this is for every state and for every subset set of state Q. What we want these two quantities, I mean the difference, to be at most 1 divided by kappa to the 3. Again, not very relevant why kappa to the 3. It works in the calculations. Okay, so let me give you then the idea of this algorithm. Sorry. If E sub I holds an oops, sorry. Okay, so the idea here is the following. If E sub I holds an N of P sub I, it's a good approximation, which was the property that we were, I was showing you at the beginning. Then this property here tells us that for the sets, actually, because here we were doing estimation for P sub I, and now we want to move to these sets X sub I, that these are going to be also good approximations, right? So, okay, let me show you how this proposition is used. Essentially, what we say is the following: E sub 0 holds because we do exact calculations, and then what we know is also that we have good approximations for this N P sub 0, right? Because again, we compute this exactly, and once we have that, we use the proposition to have an estimation of this N for this Nx0, but now for the sets actually. And the proposition tells us that we will have these approximations. And why we want these approximations? Because of the following. Once we are given a state P in Q and B equal to 0 or 1, I mean, you can define this set. This set is just the set of states or initial state Q0, such that you can reach P1 from Q0 by using, in this case, by using the label B, right, 0 or 1. And what is important here is that if you think about the language L of P1, this is going to be equal to, well, you take the language L of this set for R sub 0 of P1, and then when you are constructing this set of strings, what you have to do is you have to do it join with 0, right? And the same thing here, actually, you are doing this, you can do this, you can construct or have this set L of R1, R sub 1 of P1, and you do the concatenation with 1, right? Because this is what you are using here, 1. And the key issue here is that these two sets are disjoint. So you know that this set of this LP1 is going to be the sum of this L of this set here, R sub 0 P1, plus the size of this L of R1, R sub 1 of P1. And now what you know is that this R0 and R1, this set that you compute here, are at layer 0. And you have an estimation for that because you have an estimation for the elements at layer 0, right? So then what you know is that given that this n sub R sub b of P1, it's a 1 plus minus kappa to the minus 2 approximation of this set, the sum of these two guys here, it's going to be a 1 plus minus kappa to the minus 2 approximation, right, of this n p sub 1. Okay, what this tells you is the following. I mean, this is a summary, so you can, it will be easier to see it in this slide. You say, well, if E sub 0 holds, and you know that you have good approximations for this n for states, then what you know is that from the proposition is that you are going to have good estimations for the sets at layer 0, and then from what I just showed you, you will have a way to estimate this n for P1 by using this estimation for the sets, right? So now we have good estimations for the this set of these sets L of state P at layer 1. And okay, so this is what we have in the previous slide. So if somehow you manage to prove that E1 holds again, you will have good estimations again for these, and now for the sets at layer 1. And from there, you conclude that by using exactly the same idea, that you will have good estimation for the states at layer 2, and you keep going, right? So this is essentially the main idea. So, so then the key issue here is that if you can prove that this E sub I holds, this property holds for every layer, then you will have a 1 plus minus epsilon approximation of the the size of these sets of words, right? Okay, so then the issue is how to maintain this property E sub I, right? And the multi-sets of uniform sample play a central role on this. So Chris, sorry, how much time do I have? Probably very little.
Well, if you want questions, then you're kind of out of time, but if you want to take another minute and tell us about sampling, you can. And
okay, let me tell you about sampling okay, sorry, yeah, let me tell you about the sampling and then I will move to the conclusions actually. So the idea here is the following. So how do you do this sampling? So we need to construct this multi-set SQI of multiple samples and recall that the size, this is a multi-set that contains 2 to the kappa to the 7 words and is computed from the this sketch of I minus 1 and this set n of QI. So, and the idea here is how you compute this is as follows actually. So you do it layer by layer actually. So you start from a string WI, right, which is equal to the empty string, and then you will be choosing what is the bit going from the right to the left of this string that we are sampling. So this is the notation that we are using here. Double J it's going to be this bit B sub j, double j plus 1, right? And at the end, what you're going to have is this W0, which is an element of this L of QI. And how you do this actually is as follows actually. So the idea is the following. So suppose that you have already constructed this WI. So then you say, okay, let's consider these sets, right? P I sub B, which is a set of all the states at layer I minus 1, such that you can reach QI from this P I minus 1 by using a transition that has, in this case, label 0 or label 1. That's label P, right? Okay, so then once you have that, you say, okay, this P0I and P1I are sets of states at layer I minus 1. So so I have an estimation for these guys, and I can use this estimation. And remember, these were the estimations for these numbers. So then you will say, okay, so then how do we choose this bit? We just choose it with the probability, which is going to be, well, this n of, well, for 0 is going to be, well, this estimation of the size of the set P sub 0 I, well, divided by the size of P sub 0 I and P sub 1 I. So you use these estimations. Okay, so what is important here is that this P sub BI actually can be generalized for a set of states instead of just one state. Here we were considered this P sub I, which was composed just by one state. And why we need this idea? Because the sample algorithm is going to work as follows. It's a recursive algorithm that receives as input the layer, the set of states that we have chosen. I mean, initially the empty string, but we will have a string that we have computed actually and some initial probability, right? And it works as follows. Essentially, it says, okay, remember that we start from layer I and we are decreasing the layer. So when we reach layer 0, what it says is that with probability 5, it's going to return W0, otherwise it's going to fail, right? And if it is a layer which is greater than 0, then what it does, it just, well, compute this set, as I tell you before, compute this probability, and chooses a B in 0, 1 with this probability, with these estimations. And the important thing is that then it recursively called to the same procedure at layer J minus 1, the set P sub J minus 1, which is going to be the set that you choose here, right? The string W J minus 1. And the key thing here is that the probability that you use is phi divided by this P sub B. And why you do that, and with this I will be finishing, is just because actually at the end what you realize is that the probability that the output of sample is X, right? It's going to be, well, the probability that W0 is equal to X and the last call to sample does not fail. And this, if you see as a conditional probability, is the probability that the last call to sample does not fail, given that W0 is equal to X, times the probability that W0 is equal to X, right? And this probability is, well, you can compute it, it's just this product here, given by the sets that we use. And actually what we are going to have in the other side, when we see what is the probability of not failing, it's going to have exactly the same probability to the minus 1, right? So and at the end, you get this probability phi sub 0. And what this tells you is that this, assuming that this E sub j holds for each j smaller than I, well, if W is the output of this, to call this the sample with the probability that, again, is used that so that all calculations work, I mean, all the phi's that you are going to use are between 0 and 1, so you have probabilities. You will have a constant probability of failing, and also, I mean, the probability of that W is equal to X is going to be the same for every X in this set. So what you get is that condition on not failing, the sample returns a uniform sample from this set. Okay, so I had a bit, I mean, some additional slides here that were showing that that you can maintain this property E sub I with certain probability. So let me just go to the final remarks. So the algorithm also provides a randomized polynomial time algorithm for uniform generation. And this is coming from the fact that we are maintaining actually some uniform samples, right? But such an algorithm can also be obtained from the classical results from Jayaram, Valiant, and Basirani, right? Because the problem that we are considering when you represent as a relation is self-reducible. And something that is also interesting here is that count is Sharpie complete, but it's also span L complete, sorry, complete under parsimonious reduction, right? And well, recall that this span L is defined as a span P, and span L is the class of function computable as the cardinality of a set S, where this S is a set of output values returned by an NL Turing machine, right? So you count the number of these distinct outputs of a non-deterministic logarithmic Turing machine, right? And what is interesting here is that given that count is span L complete under parsimonious reduction, you obtain that every function in a span L admits a fully polynomial time randomized approximation scheme. Okay, so the complete version of the paper can be found with the details that I couldn't show also can be found in this at this link. And thank you very much for your attention.